Okay, so I want to give a little mini lecture here about 8.2 and critical angle. And center of gravity. So the basic idea with this is that when you have an object, right, when you have an object and you want to know when it's going to tip over. So for instance, a vehicle, right, or maybe even a pop can. I think we've all done that trick before where we have a pop can tilted on its side, right? Let me finish drawing this vehicle. So this is a car. We're looking at the back of the car, right? Something like this. Maybe you can think of a pop can. Let's see if I can draw a pop can. And we were to take the pop can and set it like this. And there's a little bit of pop in there, right? And the can is able to steady itself like this. So the idea is that this point right here is the pivot, right? This point right here is the pivot. And this works, right? And the object can stay right there when the center of gravity is directly over the pivot. And we know that to be true because there's a point on the pop can or on the car where all of its mass acts, and this force of gravity is directed through the pivot. And any force through the pivot does zero torque. And the angle that this happens at, if we were to say, let me see if I can make this clear. Say this object looked more like this rectangle I'm drawing, or square, right, around this car. And it creates an angle right here, which we can call, I don't know if I can get another color here. Right, this angle right here that we can call the critical angle. All right, so theta sub c. And the question is, well, what is that angle, right? And it's an important angle because you can think of it that if you go past it, then this center of gravity, where I drew this symbol right here in the middle, right? Our symbol for center of gravity is just this, right? Drawing on the pop can over here. You can see I drew it on the car over here, and that has to stay over the pivot. If it goes to the right of the pivot, then it's going to torque maybe if it goes to the right of the pivot clockwise, and if it goes to the left of the pivot, it's going to torque counterclockwise. And so by keeping the center of gravity right over the pivot, right, which the pivot is right here, we have zero torque, and the car balances, or the pop can balances. And so how do we think about this critical angle, right? And let me try and draw this one more time. Let's see. Maybe something like this. And we have the pivot right here, right? And then this kind of rectangular shaped vehicle. All right, so what we can start to talk about here then is that this distance right here, right, is called t. And this is, and T is something called the track width. And the reason that's important is that half of that distance, right, T over 2, is going to be very important to us. So if I draw that right there, this distance is T over 2, or 1/2 T, right? And the reason that's so important is because we also know that this distance is the height of the center of gravity. So I'm going to call that H. So what I'm setting up here, if you can't tell, is a right triangle. Whoops. And this right triangle, let's give it a little color here for the right angle. We'll go red. Right? We have this red angle, and theta critical, or the critical angle, if we think about this, let me draw it maybe in orange up here. So we have H right here, right? And we have T over 2 right here. And so what I'm trying to show you is that this triangle we're creating right there, right? That let me label a couple more things here. Let's go with blue. Maybe that's easy to see. Apologize that my handwriting is messy. This is T over 2 right here. So this side is T over 2, right? And this side is H, and this side is the hypotenuse, right? And long story short here is this angle, let me see if I can pick another color, maybe, I don't know, green. This angle right here is the complement of the critical angle. So my point is that the critical angle is this angle right here, right? And so if I come back down here and draw that, what I'm trying to say is the critical angle, which is established by where the car, how far the car can go without rolling over, right? That angle, which is right here below, is this same angle up here. So down here on this drawing, let me draw it one more time. This angle right here is the critical angle, right? And that sets up a triangle that we can work with, because we maybe we want to know H. We want to know the height of the center of gravity, or we know the height of the center of gravity, right? And we want to know the critical angle. So that's kind of the idea here, right? So if I go back to black here, and so what I'm trying to say here is this angle is theta C, right? This yellow angle. And we can say that if we think about it, it's a right triangle, right? And we have we have our formula for tan. And we learned last year that you can tan inverse both sides. All right. And the reason I'm bringing that up is because tan inverse eats tan, usually which is theta, and you get theta equals tan inverse the op over the adjacent. And we know that by looking at this triangle right here, right, which I'm kind of going to redraw really, just kind of sketch it out, that this is the hypotenuse, this is, here's my theta, this is my opposite then, and this is my adjacent. So we can say that theta then is equal to tan inverse of what? Looks like opposite is the same as t over 2. And it looks like my adjacent is h. So what we have here then in theta is actually the critical angle, is a formula right here for the critical angle. And that's what we're going to use here going forward. Okay, so another thing from the reading I just want to point out is that for a vehicle, in the chapter in 8.2, they state that a critical angle, I guess I could just call it theta sub c, that is greater than 50 degrees for a car, it is safe. Theta c is, I'll just write, is safe when it's greater than 50 degrees. So we're saying then that the car, if we see this picture of the car here, that when theta c is greater than 50 degrees, that the car is safe, right? Because if it was, say, 30, then if this car tipped up to 30 degrees, which isn't that high off the ground, it could possibly roll over at 30 degrees. We wouldn't want that, right? Because this is the angle, the one that is right here, right, that we're talking about, the smaller angle. It just so happens that because of geometry, and it's the complement of the green angle, that it's also the yellow angle up above. And so that's what we're talking about, right? Is having a large critical angle is a safer vehicle because it's harder to tip over, right? The larger the angle, the further this yellow angle on the bottom can get before the car tips over. So we want a large critical angle for a safe car. And so what creates a large critical angle? We would say when t over 2 is large, that's also safe, right? So when the track width is larger, right? Because if the track width is larger, if t is larger, then t over 2 is large. And then what about the height of the center of gravity? Well, that just makes sense, right? We want a center of gravity that's lower to the ground. So when h is small, that is also safe, right? So we want vehicles that have a low center of gravity and a large track width. So looking at the formula then, so when h is small and when t over 2 is large. So we want this number in parentheses that we're taking the inverse tan of to be as large as possible, right? It's kind of the idea, a large numerator and a small denominator. Okay. All right, so let's go ahead and look at some examples of how we use this. I'm going to go ahead and pause it for a second. All right, so let's look at an example here. And I'm going to slide this up a little bit if I can. Let's see. All right, so this is this is number 17 from the chapter. And in 17, I believe they give us, I don't have my textbook here with me, but I believe they give us a filing cabinet. And the filing cabinet, they tell us, is 52 inches tall. So a little over 4 feet, right? And I think they tell us that the width here, or its base, is 15 inches across. And I think either they tell us that the height of the center of gravity is 26 inches up, or they want us to assume, because it's a symmetrical object, that we can assume that the center of gravity is halfway up. So we know that h of the center of gravity, I'm going to call this h, is equal to half of 52, which is 26 inches. All right. So anyways, what else can we get here? We know that this is equal to t, and that we're always interested in t over 2, right? So t over 2 is going to be 7.5 inches. All right, so what's going to happen here is we're going to take this filing cabinet, see if I can do this, and tilt it. I got to get used to that line straightening out. Haven't been using this enough. So we're saying that this center of gravity is going to be directly over the pivot. And that is when the force of gravity goes through the pivot and this filing cabinet doesn't torque. Okay, so I know that's not a perfect drawing, I apologize. But we can then say that this line right here is equal to h, which is we just said is 26 inches, and this distance, or half of the base, right, is equal to t over 2, which is 7.5 inches. All right, so anyways, that sets up a 90-degree right triangle. Let me try and get some different colors here. So there's 90. Theta critical. It's this angle right here, right? And that is the same as this angle right here, because this is the complement of this unknown angle that I didn't color at all, and so these two yellow angles have to be the same because of how the geometry works out. So anyways, that's theta critical. I can go ahead and label that. So those two angles are the same. And we can go ahead and, I think the question is asking us to solve for theta critical. So we know, just in general, theta equals tan inverse op over adjacent. So we can say that theta critical is equal to tan inverse of our opposite, which is 7.5 inches, divided by the adjacent, which is 26 inches. So let me just be clear there, right? The formula I'm using is theta critical equals tan inverse of t over 2, right? Divided by h, which h is the height of the center of gravity. Oops. H is the height of the center of gravity. And not the height of the filing cabinet. I guess if it was the height of the filing cabinet, then we'd have to use h over 2 along with t over 2. It'd be t over 2 over h over 2, but whatever. However, it best makes sense for you. So then we plug this in our calculator, and I don't have my calculator with me, so you have to take my word for it that this is equal to this right here, right? If I plug this in my calculator, this is equal to 16.09 degrees for theta critical. Okay, cool. And that was number 17 there from the textbook. So let's go ahead and look at one more. Let's look at number 22. And 22 says, this is kind of an interesting problem. I think in the textbook, and let me go ahead and read. Let me see if I can correct that drawing. I think there was a problem in the textbook with this where it's like a cat walks out onto a table or a desk, and how far can, or a board on top of a table, and how far can the cat walk out on the board without tipping the board, right? So you have a table, kind of looks like this. All right, so this is just the table, and there's a board on it. Let's see. I think it looks something like this. Okay, so they tell us that, let me see if I can get a different color here, maybe orange. They tell us the mass of the board is 6 kilograms. So maybe I can just write that off to the side. I don't know, I feel like I don't have enough room, but I have tons of room. The mass of the board is 6 kilograms. They also tell us that the length of the board is 50 centimeters. All right, and they tell us that so we know then that the center of gravity for the board, right, is 25 centimeters away. So can I draw that? Well, we can say that the force of gravity for the board acts at the middle, which is about right there, right? So this is going to be Fg of the board, which is equal to, 6 kilograms times 9.81. Okay. And we also know that, I think the question states, how far can a box be placed out on a board? How far can this box sit? And when the mass of the box is equal to 2 kilograms. And so we know the box has a force gravity of, this one I probably should have drew smaller, is equal to 2 kilograms times 9.81. Okay, hopefully you can see that. All right, so the big idea here is you have two objects here, the board, right? And this board and this box up here, right? And the idea is that there is going each one has a mass, and there's going to be a combined center of mass, right? So maybe I can draw this in here using maybe green or something, and the combined center of mass is going to be when the box is out as far as possible. The combined center of mass is going to rest over the edge of the table. So we're saying then that the pivot, the combined center of mass is going to be over the pivot, and that this is going to be the pivot. So we have two torques happening here, right? The force gravity of the board, right? This is going to cause the board to torque this direction, and the force gravity of the box is going to cause the board to torque clockwise in this direction. And so what's going to happen is there is going to be a force normal, right? But it's going to be at the pivot right here, because the board is going to be ready to turn. It's going to be ready to it's going to be, you know, pretty much off the table except for its contact at the pivot. And so this is this is what we should expect. So really this is a torque balance like we've done before, and we want to know how far out on the table or on the board the box can be. I forget what the question asks. I think the question asks from the edge of the table. So how far, I think we want to know, let me see if I can label this. We want to know this distance right here. How far from the pivot, which is at the edge of the table, right? What is that distance D right there? and that's all we want to know, right? So it's really just a torque balance, kind of like we've done before in the past. So if I start off the problem just like before, drawing the free body diagram, okay, it's done. Tough thing there is knowing that force normal is acting at the pivot because it's about to turn, right? It's losing contact with the table. There's no contact where the board's hanging off. All right, but you can start it the same way, which is to state the sum of the forces in the y direction, right? Just like we did previously. So we can say sum of the forces in the y direction is equal to 0. You don't have to do this, but you can, and that means force normal minus FGB minus FG box. Oops, I guess I got to be more careful there because they're both FGB. FG board minus FG box is equal to 0. And we can say then that, I might do a little rounding here, FN minus FG board, 6 times about 10, right, is 60. Minus FG box, which is 20 newtons, is equal to 0. So we can see FN is approximately, right, 80 newtons. But that really doesn't matter. And the reason for that not mattering is FN's not going to torque the board, right? Because it's going through the pivot, right? If you look up here, you can see the pivot is, let me find a good color. I don't know. I'll go pink. This is the pivot right here, right? And so FN is right through the pivot, and it's not going to cause any torque. So we can go ahead and do the torque balance to solve this problem. So sum of the torques is equal to 0. We got 2 torques here, right? This one's going to be positive because it's counterclockwise, and this one's going to be negative because it's clockwise. And so we're saying that we have torque due to the board minus the torque due to the box is equal to 0. We know that both of these forces are acting at 90 degrees, so sine 90 is going to be what's going on. Torque is equal to R cross F, which is distance to the pivot, which is what? Instead of using R, I probably shouldn't use R, right? I should probably just go ahead and write it. Distance to the pivot, what is this distance right here, right? And I don't know if you can see what I just wrote there. So what is this distance right here in yellow? You should be able to see that. All right, we know that the force gravity of the board should act halfway, right? So this right here is 25, right? And I think the problem tells us that I think they tell us something about that. I think they tell us that that this distance to the right here from the they tell us the distance to the edge of the board, right? I think they tell us, or they tell us this. They tell us, let me get my yellow marker again. They tell us that this distance right here, also in yellow, is 20 centimeters, which I know it's hard to see. They tell us that is 20 centimeters. Because of that, then that means that 20 and 25, that this distance right here has to be 5 centimeters. So the distance from the center of gravity of the board, right, to the pivot is 5 centimeters away. It's all about the distance to the pivot here for R. So we can go ahead and say that the torque of the board is equal to 5 centimeters R cross F, which we're going to have to change that to meters, times the force gravity of the board, which is 60 newtons, times the sine of 90, minus this mystery distance in blue, which we don't know. So we're going to call that, keep calling that D, right? Because that is the distance from where the box is, right? The box is to where the pivot is, which is this combined center of gravity, right? So we want to know that this blue distance, D, well, it's kind of blue now. All right, so we can say that that's equal to, or minus D, 20 newtons times sine 90 is equal to 0. All right, 5, this is actually going to be 0.05 times 60. This is just going to be 1 minus D times 20. Once again, this is just 1. And I think if we do the math here, 20 newtons times D is equal to 5 times 60 is 300. Move the decimal 2 times. I think that's going to be 3 is equal to, this is going to be negative. So we'll kick a negative 3 over to the other side. Whoops. Let me see if I can redo that. So right here, this is still 0, and this is going to be negative 3. So we end up with D is equal to 3 over 20, right? Divide both sides by negative 20 newtons. I think this 3 had units of Newton meters. So anyways, we can go ahead and cancel off some of that. All right. So this is going to be meters. And D is equal to 0.15 meters, which is also known as 15 centimeters. And so what we're saying then is this distance, we're saying that this distance right here on blue, let me get my blue marker back, is equal to 15 centimeters. So the question asks, what is the most that the box can be out from the edge of the table onto the board, right? The furthest out. So here's the end of the table right here, right? And it can be 15 centimeters from the edge of the table is where this box can rest. So we can say the furthest out is 15 centimeters from the edge of the table, which is where our pivot was, right? If they were going to ask from the right end of the board or something like that, what would that be? Then that would be, well, this is, let's get a different color here, maybe purple or, not purple. Let's go, I don't know, gray. So this would be 25, this would be 5, that's 30, plus another 15, that's 45. And so it'd be 5 centimeters from the right end of the board, right? From this is the right end right here. And so 5 centimeters in from the right end would be another answer for where the box could go. But yeah, but that's about it. So good. So 15 centimeters from the edge of the table. All right. Hopefully there's no questions there, and hopefully that makes sense. Once again, that was number 22. And you can see just doing, we didn't even have to do some of the Y forces, but we did it anyways. So we didn't even need to do that part, and it worked out. So, all right, I think the key there is knowing that the combined center of mass has to be over the pivot, and we have that in green there, and in that then both force gravities exert a torque, and normal does no torque when it's balanced and in the box is as far out as it's going to go. All right. Anyways, that's it. Hopefully that helped. All right.